Okay, chapter 7 and 8 kind of go together. It's like almost one chapter. Chapter 7 is work, kinetic energy, and power, work and power. They go kind of hand in hand. Chapter 8 is potential energy, and conservative versus non-conservative forces, and stable versus non-stable equilibrium. So hopefully we'll be able to do this week. Finish both of them this week, and then next week start chapter 9, which is momentum and impulse. So chapter 9 will be in momentum and impulse and center of mass. So that's kind of chapter 9. Momentum, impulse, center of mass. So that's next week. So chapter a week, kind of. Actually, this is like 2 chapters this week. But these 2 chapters are like a chapter anyway. You could kind of combine them. So the work is a concept that's a definition. So this one, something that's a definition, you can't prove that. So usually we distinguish it by 3 lines, and we say, by definition, work is defined as the integral of force dotted into the displacement, infinitesimal displacement, dr, right? So that's equal to, the units of work would be Newton times meter, which is abbreviated as a joule. And in the British unit system, it's gonna be foot times pounds, feet pounds. So you do work when you exert a certain force and you drag a certain object at a certain distance, right? So you take the dot product of your force times the displacement, and then if the force is variable, if it's changing as a function of the displacement, then you integrate it. If it's not changing, then you don't have to do an integral, of course, then you just do the dot product of the force and the displacement, right? So if you take a block, let's say you exert the block some force, right? So if the force is constant in magnitude, right, and its direction is constant, and then the displacement is this way, then let's say you drag it a certain distance, right? So then you're taking the dot product of that. So the dot product means that the quantity is gonna come out scalars, right? So when you take the dot product of 2 vectors, it comes out as a scalar, which means work doesn't have a direction. But work can be positive, 0, or negative. It can be positive, 0, or negative. So in this case, is the work positive if you're dragging it like that and the object is going like that? Is that positive work?
Positive.
Yeah, exactly. So then you're gonna take force D times cosine of the angle between them, right? So then you take the theta. So in this case, it would be an example of a positive work, right? But while you're dragging it, the normal force is holding the weight up, right? Supporting the weight, and then you have mg. So the work done by gravity and the normal force in this case, if the surface is flat, right? Gravity is perpendicular to the direction of the displacement, right? And the normal force is also perpendicular to the direction of the displacement. So in this case, both of the work done by gravity and the normal force is 0. So that would be an example of 0 work. So the work done by the normal force is going to be n times d times cosine of 90, and that's going to be 0 joules. So in which case, what that literally means is that the normal force is not an active agent in this. It's not an active agent in the block going to the right, right? So all it's doing, the normal force's function in this case, is just to support the object so it doesn't fall down, you see. But it's not an active participant in the motion of the object. That's what it means to say it does 0 joules of work. But you're doing positive work, which means you're an active participant in the motion of that object, right? And if there was friction in the system, right? The other example of 0 would be the gravity in this case, right? So the work done by the normal force is 0. The work done by gravity is mg d times cosine of 90, and that's also 0 joules, okay? Now if we add friction on top of that, mu k n, so then the work done by gravity, by the friction force will be negative, right? So work done by friction is going to be negative mu k n, or I can say it this way, mu k n times d times cosine of the angle between, right, friction and the displacement, which is going to be 180, right? So it's opposite direction, cosine of 180. And generally that is the case. Friction is the opposing to the motion, right? So it's going to be 180 always. So then it's going to be just cosine 180 is negative 1. Minus mu k and d. So the work done by friction is going to be a negative work, which means that friction is an active agent in this system. It is an active agent in the motion of the object, but instead of causing the motion of the object, it's fighting the motion of the object. You see? And so I guess we could say negative work means you're fighting the motion, right? And then positive work means you're creating the motion. You're an active participant. You're causing the motion to happen, you see. So these two forces are not causing any motion. It's interesting that in the case of a centripetal force, when you're, let's say, have a string and you're twirling something in a circle, right? What's happening there? Let's say you have your hand, and then you have a string, and then it's going in a circle.
There.
The tension T, so the tension is causing the motion.
Yeah.
It is an active participant, but the work that it's doing is 0.
Because the velocity is
always
perpendicular to the...
Yeah, so velocity is perpendicular, so the displacement, so when you're going like this, the displacement is like this. Any interval displacement is like that, and then the force is towards the center. So even though the force of the string causes the object to go in a circle, so we would say the work is 0, but in this case, you're an active participant in the motion. You're the cause of the object going in a circle, but you're doing no work. So that means 0 joules doesn't necessarily have to mean you're not an active participant, you see? Here, yeah, normal force has nothing to do with the motion of the object. Here, the tension has everything to do with the motion of the object. Without the tension, it doesn't go in a circle. So in this case, what would it mean to say work is 0? So even though you're causing the motion, but your work doesn't have the potential of increasing the speed of the object, you see? All it does is provide the path of the object for it to go around, but it doesn't change the speed of the object. But then how does that happen that sometimes you make it go faster or slower?
We change the force.
I think you're changing the force by your hand,
Yeah.
and you changing the force is causing the speed to change, but that doesn't mean you're doing work. Isn't that weird? It's like work is changing kinetic energy, we say, right? So if you're changing the speed as you're twirling it, then are you doing work? Work is changing kinetic energy. Apparently not, because all you're doing is changing the tension, but the angle between the tension and the displacement is still 90. That's a weird thing, you know. it's a case where the speed of an object is changing due to the tension, due to the force on it, but you're still not doing any work. It's just by changing the tension, by lowering the tension, it goes slower. You see?
But that's the ideal situation, right? The ideal situation that our hand were not moving, but in a real situation when we like rolling things, our hands are like moving like this, so the central point is keeping moving.
Oh, because by increasing the tension. But that's just because it's normal for us to move the wrist. You're saying the wrist action.
Yeah.
Right, yeah.
So
But what if you just go like this and change the tension?
But there is still a very small movement. So
You're right,
I think
there's
it's more like
the
ideal
intricacy
situation.
of this doing this is pretty complicated. That is true, yeah. So what's going on? Well, who's doing the work on what, and is there actually a work being done? And then as you increase the force, how are you creating more tension? So by just rotating faster, you're increasing the tension on the string. Wow, it's like just that simple thing is a complicated procedure, huh?
Maybe when you're,
Yeah.
maybe when you're moving your hand, like you don't always keep the angle at 90 degrees.
Yeah, I see. There's no way, because there's no way for you to do like this without doing some rotation yourself. So there's some axis of rotation here. So you're creating a gyroscope, right? Then you have the string, and you have the object going around like this, right? But technically, the string is not doing any work on the object because the angle is always 90. Yeah.
But if your wrist was perfectly still, it would just fall.
You can't make something rotate if it's still?
Well, if it's perfectly still.
Oh, I see. So the only way for you to create a tension is to...
Otherwise, it'll just.
Yeah, exactly. That's true.
So maybe the test we're using a more like an ideal situation. So it's like we assume that it's perfect still, but like in the real situation, there is no way we can preventing the central point that perfect still.
Because like in outer space, it would stay. As soon as you got it initially going, you could just hold your hand perfectly still, and it would just keep going around, right? But because of gravity, we have to counteract that effect. You know?
Is that because of gravity?
Well,
Yeah.
I don't know how centripetal force works in outer space. Like if I spin something, doesn't it just keep going around, or does?
Yeah, I mean, if I'm giving it force, I
Yeah.
could make something go around. Yeah, definitely.
But no, like if I give it initial force, would it eventually?
Stop? No, there's no friction.
Yeah. So, okay.
Now, later when we get to the chapter on conservation of angular momentum, way towards the end, we'll see problems that look like this. Imagine these markers haven't been used, so they're all drying up for the week. So it's like this. Let's say you have something like this. So let's say this 1 kilogram object is lying on a frictionless surface, right? And then it's supported through a hole, a tiny hole with a 2 kilogram. So now in this case, this 2 kilogram object provides a tension in the string. So you don't have to do this. Just by it sitting there, it provides a tension, right? So all you have to do is just give this enough of a kick, right? Like that. And then it just goes in a circle. And if you give it the right kick with the right velocity, it could go forever on a frictionless surface. You see? Now, would the string do any work on that?
No.
No, if it's going forever and the radius is never changing, it would do no work. The velocity would stay constant, right? What would the tension in the string be? 2 times 9.8, 19.6, then that's T. So the tension would just equal 19.6, right? And then the tension would pull on this guy. So tension equals mv squared over r. So 19.6, right? And then if that is 1 kilogram, right? So 1 kilogram velocity squared over r. And then the r is the radius of the disk. So 2. So that's the velocity that you have to give it in order for it to stay in the radius. You see?
So,
Will there be friction?
No, I'm assuming there's no friction.
Oh, okay.
You know, yeah. 2 times 19.6 and then square root of that.
so if we were in outer space, why couldn't we just use this as a generator? If it spins around forever, couldn't we just use that with magnetism to create electricity?
Not everything that moves creates it has to be, you have to have a magnet that's moving through coil. To make this into a generator, you have to give it some thought.
Like, couldn't we just have the magnet, like with the initial kick? in the
Oh,
center?
wait a minute. In outer space, you don't have gravity 9.8.
Oh.
If you're completely, well, I'll put it this, it depends how close you are to the Earth. If you're somewhere here and the Earth is here, you do have gravity, it's just less.
Yeah.
But if you're way
Yeah.
away from anything, you know,
Yeah.
then of course this is nothing and then you don't have tension. So everything is just floating.
Right.
So you can't create the situation in outer space.
Even with the initial kick, when,
Well, what would happen, with an initial kick, it would just go in a straight line. And it will pull this up and then this would hit this.
what
Because
if,
the objects like to go in a straight line, right?
right,
So if you give it a kick in outer space, there's no gravity pulling this.
Right.
So this guy says, I don't care what you do to me.
Yeah.
This guy says, I want to go in a straight line. This goes up and then hits the disc, you
Oh.
know.
but if we tethered it like to a center point, like, I guess
Block?
the friction of whatever is in the center would slowly slow it down, huh?
I'm assuming something is holding this disc in place, of course, you know,
Yeah.
some mechanism.
Yeah.
Yeah.
That seems like we can make something out of space this way. Because,
To create
yeah,
perpetual energy.
well, not perpetual, but
You
like,
can never defeat entropy.
No, no.
Not even in
But
outer
I
space.
mean,
You
if we-
give that up.
If we gave it like an initial kick with like combustion or something, like, let's say you had a bullet tied to a string, metal rod, whatever, and you fired it, wouldn't it just kind of just keep spinning for a long time before it slowed down?
But what is it connecting to? A string?
Like something in the center.
Oh, just hold
Like-
it with a pin or something?
Yeah, I mean, I'm
Then
assuming,
just shoot this, and then it'll go around forever?
yeah, just whatever I guess the friction on that center point would be the only thing. that would
Yeah,
slow
I
it
know,
down.
I see what you mean, yeah, then
But
it'll
the-
just go, but that you could even do on the Earth, as long as you have a frictionless surface.
Right, that's true. How come,
Well, in outer space, it would be easier to have frictionless
Yeah.
surface because there's no normal force,
right,
right?
exactly.
Because friction is, remember, mu Kn,
Yeah.
right? So yeah, what you're saying, it doesn't make sense.
Okay.
But how do you use that as a way of creating energy? Then you have to come up with some mechanism,
Well, I mean-
like the object has to be magnet, and each time
Yeah.
it goes through a coil of wires,
Yeah. Well, like-
creates an electricity.
Like any motor or generator, isn't that how they work on inside? There's coiled wires, and then there's just a magnet.
But that
loose.
coil of wire causes heat in the wires that it creates. That heat dissipates into energy.
Okay. I hadn't thought this through.
Yeah, not everything is 100% efficient, so I mean, eventually,
I'm just thinking.
yeah, you can never defeat entropy, basically.
Yeah, but I mean, it seems like it'd be a good way to.
The
I
only
mean, I
thing that
guess-
helps go against entropy is gravity,
Yeah.
because gravity collapses gases into stars, and then because of stars, we have life available.
Yeah.
So gravity goes against the rest of the universe's desire to go to disorder.
Yeah.
Gravity is the thing that causes life to exist
Yeah.
because it creates stars.
I actually saw a documentary.
But even with that, it doesn't do a perfect job because the eventual fate of the universe is all black holes. And,
Yeah, I was gonna
you know,
say, I saw this thing where there's like a black hole at the center of like almost every galaxy. And they just realized that recently that they're at the center, there's usually a black hole.
yeah. So that means the universe eventually will have its way.
Yeah.
Okay, so then what we're gonna do is to that problem, we're gonna add, once you find out the velocity that it has, then we're gonna add another weight as this thing is moving. Right? We're gonna add another weight, and then we're gonna ask the question, what's the final velocity of the object, and what's the final radius of the object? So as you give it the right kick and it's going, what happens when you add more weight? So you increase the tension, and this thing, I think it starts going inward, right?
Right.
So as it's going inward, is the velocity changing?
Yeah.
Yeah,
Hmm?
go.
Some intriguing stuff are happening, right? Because you have to also think about conservation of angular momentum,
Right.
right?
MBR.
MVR, right? Angular momentum is MVR, right?
Right.
So the reason I brought this up is it introduces this whole concept of, is the work done zero or is the work done not zero? So in this case, is the work done by the tension zero as this thing spirals inward? So let's look at it from a top view. Top view. So this is the tension, imagine. So as it starts spiraling inward, what is its path gonna look like?
Like an inverse.
Slightly inward, right? Not, it's gonna be less than 90 degrees here, the angle. So then its path is gonna look like this,
Ellipse.
like almost like a helix. And then until finally it settles down to some new radius, right?
The Fibonacci sequence.
Huh?
No, it just looks like the Fibonacci.
Yeah,
sequence.
Fibonacci, yeah, exactly. So now, is the tension doing work?
Yes.
Yes.
Because the
It is doing work.
angles.
Because
less
the
than
angle
90
here is
degrees.
less than 90, right? So no matter where the object is, the tension is always towards the center of the circle, right? But the velocity is tangential to the path, and that angle is always less than 90 because it's spiraling inward. So is the work positive, zero, or negative? Which one is it?
Positive.
Huh?
Positive.
Positive? Yeah, it's more like this scenario, right?
Yeah.
Yeah. So that means the tension pulling in, this angle is less than 90, not greater than 90.
Yeah.
So if it's doing positive work, what should happen to the speed of the object?
Faster and faster.
Faster, which means it conserves angular momentum. You see? The angular momentum, mv1r1, mv2r2. Right? So the v2 goes up,
The R2.
R2 goes down. So it's interesting. We argued here in a kind of let's see. We argued not so much from an angular momentum point of view. We argued from a work point of view. We said, as you add weight, it spirals inward. So now the tension that usually doesn't do work in a circular motion begins to do work because the angle is less than 90, right? So then from there we concluded that the velocity should be increasing as the radius decreases. So almost as if we proved the conservation of angular momentum indirectly, right? But then to really prove conservation of angular momentum, you have to go to the definition of angular momentum, R crossed into the linear momentum. Okay? So if something is going like this, linear momentum is mv. If an object is going around a circle, right? And this is the vector r. So the definition of angular momentum is r crossed into p, out of the board. It's a vector that's out of the board. So to say angular momentum is conserved is to say r crossed into r crossed into p is a constant. Okay, but what thing changes angular momentum? Torque. Forces change linear momentum, and torques change angular momentum. So it's almost like I'm giving you a whole overview of what's about to come for the next 4, 5, 6 weeks. All right. So forces change linear momentum. So if there's a force on an object, its linear momentum changes, and if there's a torque on an object, its angular momentum changes. Right? Torque, angular momentum. So if you want to prove something's angular momentum is conserved, you have to prove that there's no torque on it. So if the angular momentum is conserved, there should be no torque. So if T is 0, L is 0. So what we did, even though we're saying, oh yeah, R is going, when the R goes down, V goes up, because the tension does work. But that's not a formal proof that the angular momentum is conserved. We're just conjecturing that possibly the angular momentum is conserved, right? So to really prove angular momentum is conserved, what do you have to do? Prove that the torque on the object is 0. So, is the torque on this guy 0? What's the definition of torque? Then now you have R crossed into F. So you have definition of angular momentum, torque, force, and torque. Force is dp dt, torque is dl dt. So if the torque on an object is 0, then its angular momentum is conserved. So what's the torque on this guy, right? So let's first do the torque on the guy if the object is going in a constant radius circle. If it's going constant radius, what is it? You got the R like this, right? And the force of the string is like this, right? Force of the string, the tension is like that. Right? So what's the torque as it's going around? So imagine the hole is very small, right? So if the radius is constant, you can say, okay, the torque is 0, the torque is 0, right? And therefore now you can conclude that angular momentum is 0, right? Then you can say angular momentum is constant. Well, if that's the case, mvr1, mv2r2 is the same, then the mm cancel. So of course, in that case, if the radius is not changing, what's going to happen? R1 will equal R2, and then V1 will equal V2. That means the velocity will never change in a uniform circular motion, right? But what if the thing is spiraling inward? What if the thing is spiraling inward? What's going to happen then? Is there going to be torque? So now imagine just a random location of the object. What's R? R is the vector from the center of the hole, right? All the way to there, and then tension is towards the center. Still 0. So whether it's spiraling inward or not, the torque didn't care about it. R, T. Because the angles that matter are the angle between the radius vector, which is from the hole to the object, and the tension T. So whether the object is spiraling inward or remaining constant radius, both cases the angular momentum is conserved. Therefore we can now say, okay, even though the force does work on it, the work that it does not cause its angular momentum to change. And therefore, the ratio of V1 to R1 is the ratio of V2 to R2 times R2. You can see that's the formal proof that the angular momentum is conserved.
Also,
Okay.
I have a question. Angular momentum is a vector or?
It's a vector, yeah.
It's a vector? But why you say like it's a constant?
Because there's no torque on it.
There's no torque on it?
Yeah.
So it's a vector. I know it's a vector like that, right? Using.
Yeah, exactly. As long as there's no torque, as long as this is 0, in those cases where the torque on the system is 0, then you can conclude the angular momentum is constant.
Okay. But angular momentum, always conserves it.
Angular momentum is conserved only if the torque is 0.
The torque is 0. So if that's not, let's say R and T doesn't like go against each other, it's not 0.
Then it's not 0.
Okay.
One time I was, I forgot when, many years ago, maybe 1910 or 1915 when I was a kid. You know, I was offered this scholarship, or I think it was an internship or a scholarship. So when I went, they interviewed me. What do you want to do? Which university do you want to go to? All those good questions, you know. And then they asked this physics question. And I think I got it wrong. If I remember right. So I didn't get the money, okay? And the question was like this. They said there's a post, like a big thick post, and there's a chain around it. And the chain is sitting on an icy surface with length L, right? And then an ice skater comes with an initial velocity v, comes and picks up that chain, right? Picks up that chain, and as he picks up that chain, he starts going like this, and then the chain begins to wrap around the post, right? Like this, like this, like this.
Right.
And then by the time that he's in this location, L/2, he lets go of the chain. Then he continues going forward. So what's his final velocity as compared to his initial? This is exactly what I had to figure out. I mean, right on the spot, they asked me this, right? So I had to figure out, is there work on it? Is it the tension of the chain doing work on him? And is it causing a torque on him? One or the other is zero, right? If the thing is doing work and there's no torque, then the angular momentum is conserved, right? If the work is zero, but the torque is not zero, if the work is zero, then V final is V, right? So basically, it ends up that my answer was, I thought there is no torque. Did I say that right? Yeah, I thought the torque is zero, but the work was positive. So similar to that guy, right? So if that's the case, I would have argued that V final is what? 2V initial. So essentially, I argued the same thing as that, right? When this one, there will be initial, if the radius goes by half, the velocity should double, right, you see? Because the velocity should increase because the tension in the string is doing work. So my argument in my mind is that this is similar to that, right? It ended up being exactly opposite, okay? So the answer was V final was equal to V initial. And then when they told me that, I go, what the hell? It's the same velocity? I go like that. There's no work done on the object? They were right. Okay. So as it picks it up, so just imagine like any location, right? So you have a tension T and velocity V. You see? So what's happening in this case is that the pivot point, as the chain moves, it's moving around the pivot point that's at the edge of the object, right? At the edge of the post. So the motion that you're making is always perpendicular to that pivot point. You see, where the chain is touching the post. So that angle is 90. Isn't that weird? So by the time the chain is like this, it's a little bit shorter, right? So this is V, this is T, still 90. That motion of that object is very different because the hole is fixed, right? Set center. Then you're spiraling inward, the angle is less than 90. See, something small like that detail, oh my God, I had to think about it. And then he said, do you notice that there is a torque? I said, really? There's a torque on them? He goes, R crossed into T. The angle is not 180. The motion of the object is going around the center of the post. Right? And the tension is this way. So actually there's a negative torque. Why? Because his angular momentum is in which direction? His angular momentum is going like this. It's out of the board.
Right.
Right?
Right.
Which direction is the torque? R
R.
crossed into the board.
Yeah.
So the torque caused by the chain, the force of the chain is negative, while the angular momentum is positive. You see? So the angular momentum is mvr, right? V is this way, R is this way. R crossed into mv is out of the board. And then the tension into the board. So that means there's a negative torque, right? Torque is negative, and it decreases the angular momentum, right? So because of that, his velocity stays the same. His initial angular momentum is mv initial r, mv initial l. His final angular momentum, mv initial l over 2. So the angular momentum decreases by half. But the energy of the system stays the same. Beautiful. So that and that are complete opposites. One case, the tension does work. One case, the tension does no work. He goes, sorry, that was a hard problem. That's hard to realize. Okay, but then he goes, okay, we'll let you know if you won the scholarship. And then, of course, you get the letter like, thanks for applying, and there were many other good candidates like you. Blah, blah, blah. Right? That's why all that detail and understanding matters. Okay, so now next thing we have the proof of the work energy theorem. So we have F work is equal to F dotted into D. Then you have here Fx I hat plus Fy j hat plus Fzk hat dotted into dx I hat plus dy j hat plus dzk hat. So then you have here Fx dx plus Fy dy plus Fz dz. Right? So if you're traveling in a certain random path, you're just going to take the force in the x direction times the distance in the x direction plus the force in the y, distance in the y, plus Fz dz. Now if the force is varying as a function of the displacement, then you do an integral f of x dx plus f of y dy plus f of z dz. Right? So what is this equal to? Well, we can use the equation F equals ma. may dy plus maz dz right? And then what is ax equal to? Ax is dvx dt, right? dvx dt times dx plus integral mdvy dt dy plus integral mdvz dt times dz. Right? Then what's that going to equal to? So basically we're starting from the definition of work and saying, okay, if work is defined as this, then here I'm using the equation Newton's law. Fx is the rate of mass times acceleration, right? Then I'm going to take this and slide this dt under the dx and write it like this. mdvx dx dt. Can I do that from calculus?
Yeah.
Can I slide this here? Well, it's kind of like not just calculus, in math you could do it too. You can say like 5/3 times 2 is the same as 5 times 2/3. That's kind of like you're taking this and sliding it under here. You see what I mean? Is that true? 5/3 times 2 is 5 times 2/3? Yeah. So you just take this, put it here, and do the same thing to the other ones. Then what's that going to be? Well, dx dt is vx, velocity in the x direction, right? So then this became vx, and then I wrote it before, and this is already dvx, it was already there. And I have here m dy dt is vy, dvy. Okay, then what's going to happen? Well, this one is going to be integral of like half mv squared, right? Half mvx squared. Half mvz squared, right? So what we did is we just proved the work energy theorem, which is to say when the force does work on an object, then the kinetic energy of the object changes. Because this is the total kinetic energy of the object. Vx squared plus vy squared plus vz squared is equal to what? V squared. Right? So the kinetic energy is defined as 1/2 mv squared, and it's also in units of joules. Right? So if there is an initial kinetic energy, then you can say 1/2 mv final squared minus 1/2 mv initial squared. So therefore, the total forces, the total works on an object equals to the change in kinetic energy of the object. Now, in chapter 7, we don't even have to refer to potential energy. We can just do everything by work and kinetic energy, right? But in chapter 8, then we introduce the idea of potential energy, and then certain things we can do in potential energy, okay? Okay, how about the idea of power? What's power? Power is the rate at which you do work, right? So instantaneous power is going to be dW dt. It's the rate at which you do work, right? So then how do we get that here? It's almost like differentiating. It's like saying work is equal to fx dx, right? So dt d of so it's going to be a d, and then work is going to be f. Let's write it as fx dx. So then it's going to be it's going to be fx times dx dt. So it's going to be fx times v. So I factored out the fx, then I take the derivative of x dt, right? And then you have here v. So force dotted into the velocity gives you the power, the rate of work. So instantaneous power is the dot product of force with velocity. So let's see if that has the right units, because it has to have units of what? Work divided by time, right? So the units for that is joules per second, which is 1 watt. Or in the British unit system, we say 550 foot-pounds per second is 1 horsepower. 550 foot-pounds per second. So those are the most common units of power, watt and horsepower. So if you do force times velocity, will it have that units of joules per second? Let's see here. Force is Newton, and then velocity is meter per second, right? But then Newton times meter is a joule. You see the top. Joule per second, oh, watt. Cool. Let's see. Okay, so that is the power. Oh, and then let's talk about the work done by gravity and spring. Those are two common forces, so, and friction. So we saw the equation for the work done by friction is what? Negative mu k n d. That equation occurs quite often because it's the force of friction times the distance that the object travels, and then the negative comes from cosine of 180, right? Friction is always opposed to the motion. How about the work of gravity? Is there a general equation we can use for that? That's kind of quick. Well, we can say if a block is moving down an incline, right? So gravity is this way, mg, and the distance that it travels is like that. So the work that gravity does is positive, right? Because you have the force times d times cosine of that angle, right? So it's going to be mg d times cosine of theta, right? So it's going to be kind of like this case where you had a block and you were exerting a force like this, and then you did fd cosine 180, right? And then the force did positive work. Well, this is kind of this thing inverted, right? It's like this is going this way, right? The displacement, and then the force is down. But the angle is still less than 90. So gravity is doing positive work when a block slides down the hill. So in this case, gravity is the reason that it's going down the hill. It's a positive, active ingredient in doing the work. But is there a quicker equation than this that we could use? And the answer is yes, mgh, the height. So you don't really care about the distance and the angle. So you do a little bit of trick and you argue that all that matters is the height of the block, not the horizontal distance. How can I prove that? Well, just do a little triangle, right? If this is the displacement of the object, and this is theta, and this is the height of the block, right? What's d cosine theta? H. So that means the work done by gravity only, it doesn't matter. If something is going like this, all that matters, see, because gravity is down, all that matters is how much the object is moving down, not how much it's going this way. You see? So when I throw something in a projectile motion, how much work did gravity do? You don't care about the horizontal direction that it went. You see? It started here, and it went down to the bottom, right? So it's the same work that it would have done if I just dropped the object. You see? Because ultimately all that matters is it started here, and it went there, right? But if you want to be more detailed about it, you can say, okay, as the object was going up, gravity did negative work, negative work, negative work, negative work. Now gravity does positive work, positive work. When it comes to the same height, the work done by gravity cancels. Then it starts doing what? Positive or negative work? Positive. Yeah. So it's the same thing that you would get if you just dropped it. You see? But how about the work done by air friction? What would that be?
In the horizontal direction.
It's like this, like this. The direction of air friction is always opposed to the motion, right?
Mhm.
So it would be what?
Always negative?
always negative, right?
Yeah.
So then you would be what? And imagine you dropped it from this height. And then this is the distance. And then air friction is like this. Let's say air friction is negative BV. Right?
Yeah.
And then this is the displacement. But it does work all the way over there.
Yeah, it's always like the counteract direction of the motion.
Yeah. So how would we find that? Ooh, nice problem for the next test. I love that. Okay. The work by gravity is just mgh. It doesn't care about anything, right? Okay. How about work of the spring? Maybe let's do that one. Why not? Anything that's hard, we're not afraid of it, we tackle it, right? We face it head on. Right? How about work of a spring? If I compress a spring a certain amount, X, and I let go, how much work does it do until it releases the block at that point? Right? So the spring exerts a force kx, right?
Right.
So to be technically true thing, it's negative kx, right?
Yeah.
Because if x is negative, right? If x is
going-
negative, then the force is negative kx, which means it's positive, right?
Yeah, right.
So if you compress it, the x is negative. And the x is usually measured from the equilibrium point, okay? So let's say I had something like this. Let's say this is the equilibrium, x is 0, and this is x initial, right? And then the block goes all the way to here. How much work would the spring do if the final position of, well, you know what, let's do some general random position.
Random?
Let's say this is x initial, and this is x final. What's the work done by the friction? Sorry, not friction, work done by the spring.
The force is changing.
So it's gonna be, the force is gonna be negative kx dx, right? And the force is changing. So what are the limits of the integral? From negative x initial to x final, right? So negative x initial to negative x final. I don't think it's gonna matter that I put negative because the integral of this is gonna be square anyway, right?
Right.
So, work of the spring. I think I can just put positive, you know? So then what are you gonna get? You're gonna get negative k x squared over 2, x initial to x final. So then it's gonna be negative k x final squared over 2 plus k x initial squared over 2. Is that true? Well, the way that we can test if this is right or not is to put x final as 0. In other words, what if the final position of the block is the equilibrium position? How much work should the spring do? If x final is 0, then what's going to happen? The work of the spring is going to be what? This part is going to be 0, right? So then you're just going to have this. Is that right? Does that make sense? Yeah, because the work that the spring is gonna do is gonna be positive, you see? it's gonna, the spring is pushing it this way, the force of the spring is this way, and the displacement of the object is in that direction too, you see? So it's the spring is the active participant in the motion of the block. It's the reason why the block is moving to the right. So the work done by the spring will be positive. Yeah. Okay. So this half kx squared is a commonly used concept. It's the work done by a spring, or in chapter 8 we can call it the potential energy stored in a spring. Right? Okay, so let's do a couple of problems with gravity, this, and all the stuff we've talked about. So let's say you have this kind of a scenario. Okay, first question is, at least how much okay? So if you move it 0.2 meters more than that, what will its velocity be when released and it reaches x is 0? Where will its maximum velocity occur and what is it equal to? So I have some friction here that I added. Mu s is static coefficient of friction, and mu k is 0.3. So first I have to compress it, right? Some amount. In order to beat what? In order to beat the static friction. Because the spring is exerting the force, but the static friction is counteracting that, right? So how much, at least how much should I exert so that the motion begins, right? So how do I set that up? So at the point where it's, that I put it, what is it gonna be here? So then it's gonna be the force this way is gonna be what? Kx, or we can say, well, let's just leave it as kx for now, and then that should equal to what? Equal to the friction force, right? Kx, and then the friction force is mu Sn, the maximum friction on it, because as you're moving it more and more, what happens to the friction? It increases, 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 until it reaches the maximum possible that it can equal, right? So the maximum possible is mu Sn. So the K that I gave you is the spring constant of the spring, right? Newtons, 20 newtons per meter. It gives you the stiffness of that spring, right? How stiff it is. Then you 20x, and then the static coefficient of friction 0.6. The normal force is what? 2 times 9.8, right? There you go. That's how much you should at least compress in order for it to move. So 0.6 times 2.6, 2 times 9.8 is 19.6. So the weight of the object is 19.6 newtons. And you divide that by the 20. Okay, that's gotta be like 0.5 something, huh? 0.588. That's quite a bit, 58 centimeters. So that's the distance from here to here, not from the wall to there. You see? It's measured from the x is 0. 0.588 meters. I'm assuming, of course, that the spring is long enough for you to compress it that much, you know. So if you stretch it more than that, what's going to happen? Then the friction, then the force exerted by the spring is going to be more than that, and then of course you're going to defeat the static friction, right? If you leave it in the middle, what's going to happen? Nothing. This static friction is going to be 0, and the force of the spring is going to be 0. So the more you displace it, the more the spring exerts a force, and the friction force increases until you reach that point. After that, the friction force converts to kinetic friction. You see? So then it says here B, if you move it 0.2 meters more than that, then you let go, then what is its velocity when it reaches the x is 0? So how much work is what's the equation? The total works done on the object by all forces, right? Work of the spring, plus this time the friction is doing work on it, right? So work of the friction is equal to change in kinetic energy. So how much work does the spring do? Well, we said that if the final point is the equilibrium, remember here, if x final is equilibrium, then the work done by the spring is just half k x initial squared, right? Just this is x final is 0. So in this case, we can use that shorter version. So half k x initial squared, what's going to be the work done by friction? The friction force is constant. It's just mu k n, right? And then the distance that it went is also the same as the x initial, right? So mu k n times x initial, that's equal to change in kinetic energy, which is half mv final squared, and then minus half mv initial is 0 in this case, right? Half mv final squared. There you have it. So the idea is that the spring does work, the friction does negative work, and that's equal to change in kinetic energy. So then let's put all of it in. K is 20. So what's x initial? Well, the problem says I'm moving it 0.2 meters more than the minimum, right? So the minimum was 0.588, so that would be 0.788, right? 0.788 squared minus mu k is 0.4. Normal force is 19.6. .788. Mass is 2 kilograms. Is it possible that it never makes it to the center? Like you let go here, it picks up speed, then slows down, and then never even makes it to the center.
Possible.
Yeah, because the friction coefficient might be large, and it might be that it increases and it decreases, and before even getting to the center, it stops, right? So how would we know? If this comes out imaginary number, right, if this is negative, that means it stopped before reaching the equilibrium. Nice problem. You could play around with different coefficients of friction, you know.
It's 0.788 because of the 0.2.
Yeah, because I moved it, I compressed it 0.2 meters more than the minimum.
Yes, it never reached.
Is it imaginary? Never reached?
No.
Oh. V final, imaginary. Well, I guess the problem would then say, if the V final is imaginary, well, where does it stop? You know?
Yeah.
Where does it stop? And then we can still answer this question though. Where will its maximum velocity occur? Because what should happen is it's gonna pick up speed, reach maximum, then as it goes, it's gonna stop. In other words, because here the spring is doing work, but friction is always opposing it. And if the friction coefficient is large, then it might never reach there.
I actually got an answer for
Yeah, I
that.
didn't get an imaginary.
Oh, you did get an answer,
Yeah,
okay.
I got,
Well,
0.1775.
okay, then that's good.
Yeah.
0.1775. I think if this was less, like 0.1 meters more, maybe it wouldn't reach, you know? But since I stretched it 20 more centimeters, I'm giving the spring enough of a chance, you know? Okay, so that means it does reach the center. Okay, now we can answer, where will its maximum velocity occur? So probably what's gonna happen is, it's gonna reach maximum somewhere here, and then maybe slow down a bit, so this is not necessarily the maximum. So how would we find that out? What if we come up with a general equation for V final as a function of how much it has gone? Not necessarily, because this equation only applies when it's gone fully all the way to the unstretched position, right here. But what if I find a general equation from starting with x initial all the way to x final? You see? Then I can take the derivative of that, set it equal to 0, and then find out what x final maximizes the v, right? Then that'll be the way to do it, you see? So in other words, if it starts with an x initial of 0.788, right? All the way to some x final, what's the general equation for v final as a function of x final, right? And then try to maximize that equation, right? So then I can say the general equation for the work done is this equation, right? negative x final squared over 2 plus k x initial squared over 2, right? So that's the, so it's going to be the work of the spring plus work of friction half mv final squared. And then the mass is 2 kilograms, so that cancels. So what's the work of the spring? K x initial squared over 2, right? Minus k x final squared over 2. Right? And then what's the work of the friction? Minus mu k n. It's the distance between them, right? How far it's traveled. So how do we, what's the equation for that? X final minus 0.788? Or X final, or I could put, how about if I put 0.788 minus X final? Because X final is going to be a number less than 0.788, right? But if I do 0.788 minus X final, you know what? I'm ignoring the fact that X initial is negative and X final is negative, but I'm just taking the absolute values for now. I think we can just deal with absolute values and not care about the fact that they're to the left. You see? Let's just imagine the left position means positive. Doesn't have to be negative. So this is positive, positive. So that way we avoid negative. So then you're going to have here 0.788 minus X final. So if X final was 0, what would happen? The work of friction would be negative mu k n 0.788, which will come to this. You see? That's the full force of friction, the full friction work done if X final is 0. That's equal to V final squared. So then I'm going to put the K, which is 20 over 2, that's 10. X initial squared is what? 0.788 squared minus 10 X final squared minus, what is this here? 0.4 times 19.6 times 0.788 minus X final equals V final squared. So now if this equation is right, if I put X final as 0 and 0, that should get me back to this equation, right? Half 20, so that's going to be 0.788. So then you see it comes out to this. Yeah, it's great. So that means this is the general equation for V final, depending on whatever the X final is. You see? So then I can take the derivative of this. The derivative of this, set it equal to 0, right? Because whatever maximizes V final squared will also maximize V final. I don't need to take the square root of this, you know. So just take the derivative of this, V final squared prime. So then it's going to be negative 20x final, right? And then what's this going to be? Negative 0.4, 19.6, and the derivative of this is going to be what? Negative 1. Right? Because the derivative of this is 0, and the derivative of this is negative 1. Then set this equal to 0. That X final will maximize the V final, right? When it reaches that. So then what's that equal to? This one goes over to the left. What is that?
0.392
point.
392.
Yeah, does that make sense? Oh, yeah. So that means it's, right here is where the maximum occurs. 0.392. At that point, it has the maximum velocity. Even though it hasn't gone the full distance,
Yeah.
the spring hasn't done enough work yet. But friction also hasn't done enough work, because friction is fighting against the spring. You see? So they're competing against each other. Okay, now take this and put it back into here, and back into here, and find the V final. And you should get a number bigger than 0.1775. Right? So take this, put it into here, put it into here. It's kind of hot in here, right? We should call the plant facilities. It's the AC's not working. So when you do that, and when you take the square root of that, the answer here should be probably something like 0.2.
1.252.
That much bigger?
I don't know, I'm doing it again.
That seems too much bigger.
Yeah.
Yes, it is. What is it?
1.252.
1.2 meters per second?
Yeah.
And immediately it slows down after that?
Wasn't that?
That's quite slow.
But isn't that squared? Or
Did you square root it?
Yeah, square root.
Oh, okay.
Bizarre. 1.212.
252.
That's very weird. So from here to here, 0.392 goes 1.2 meters per second, and then from here to here slows down all the way to 0.17. You sure we did that right? Yeah? 110, 178. Doesn't seem right, but maybe. Are you putting this in here also, subtracting it from here? Yeah? Interesting. Okay, let's do another problem. So I guess that was right. A lot faster. So let's say you built this electric car and you put batteries in there, 9 volts, and it's the resistance of the and then you put a little circuit in there. The resistor is 2 ohms. So it creates a little power, right? And then this car goes up the hill, starts going up the hill. The angle is 20 degrees. And then let's add a little friction. Mu k is 0.2. So after 2 seconds, where will it be? And what is its V final? So this little battery is providing enough power to power it going uphill, right? It's like a little engineering project. You can build a car with an engine, right? So what's the equation for the power of a circuit, Alan? Right?
P equals IE.
V squared over R, right? Voltage of the source. Power is going to be voltage squared divided by the resistance of the circuit, right? So that 9 squared over 281 over 40.5 watts. You're producing 40.5 watts of power of the engine. Right? So now how do we put that into our equation for work of friction, work of, so what was our equation? Force, work is equal to change in kinetic energy. So how many things are doing work on this guy as it's going up? Well, the engine is doing work, right? So it's gonna be F engine times the distance that it goes, right? Times the distance that it goes. Then friction is doing negative work, right? Negative mu k n d, right? As it goes up. And then what else is doing work? Starts with G, gravity, but gravity only cares about the vertical height, right? So it's doing negative work or positive work?
It's fighting against it, so.
Exactly, fighting against it. So negative mgh, right? And then that's equal to what? Kinetic energy, 1.5 mv final squared. Okay? So,
You need the mass of
oh yeah, I need the mass of that, right? So let's do the mass is, let's say 1 kilogram. So what does it mean to say the power is 40.5 watts?
So the work is power times T.
Work is, the work is equal to force times distance, but then divided by time is power, right?
Right.
Power is 40 F times D over T.
Mm-hmm.
So that means if the power is
40.5.
40.5 watts, but you know what though, the distance that it's gonna go is also affected by the friction and by gravity. Mm. Force that's the distance. Force times velocity. Oh, okay, you know what? Power is 40.5 watts. That's equal to the force of the engine. Remember what I said, the instantaneous is force times velocity. This d over t is velocity. right? In other words, the 40.5 watts is the force of the engine times the velocity,
Mm-hmm.
and the force of the engine is gonna be constant. This force of the engine is constant, but the velocity is increasing. No. Velocity is increasing.
So let's say the initial velocity is given by that formula, and you just kind of like turn off the power once it gets energy, and it keeps going up. Is it possible?
This problem, maybe I didn't give you enough information. In other words, I have to say, is this force constant? Is this velocity that is going up at constant speed? Because you could have a car
at a
that's just going at a
constant speed.
constant speed,
Okay. or
or you could have one where it's almost like a car, where you get in and you press on the gas pedal and you accelerate, you know. So it probably has to give you a little bit more information. So let's say it told us that
As a function of
the
time.
car is going up at constant, if it goes up at constant speed,
then
then
the work is zero.
then it would be like this minus this is zero,
Right.
right? It's going at, let's see
As a
here.
function of time.
If it's going up at, let's see here, at constant speed,
Kinetic energy is zero.
then the change in kinetic energy would be zero, right?
Mm-hmm.
So this would be zero. Then what could we do with this part? Then we can answer, well, how far is it gonna go in that point, you know? So then we can say here, F engine D, so 40 is equal to F engine times V. F engine is gonna be 40.5 over, so then the F engine is gonna be 40.5 divided by the V, right? Times D minus mu K, and D minus mgh equals 0. Then the H is related to the D, right? So if this is D, H is just gonna equal D sine of 20, right? So how many unknowns are there in this equation? Could we solve for actually the D factors out, right?
Mm-hmm. Then,
D factors out,
right. So we can solve for V.
so then we could say 40.5 over V is equal to mu K N plus mg sine 20.
We can solve for V.
We could solve for V. Then we could say, well, in 4 seconds, how far would it have traveled at that velocity?
So it's VT.
So in this case, it's a more constant speed case,
Uh-huh.
but you're using the concepts of work and you're bringing in the idea from electricity. You see? So then we could say V is equal to 40.5 over, and then the mu K is gonna be, what is that, 0.2. And then N is gonna equal what? Well, if it's on an inclined plane, what's the N equal to? Mg cos theta, right? mg cos theta, don't forget that. So n is, what's the mass here? So 1 times g times cos theta, right? That's this. And then plus m times g times sine 20. There you have it. So that's going to be the, in other words, if the power, what have we solved here? We've solved if the power of this toy car is 40.5 watts, that's the velocity at which it will go up on this ramp. I think the engineering department has a class, don't they? Where they make you, where he has a project that they end with this. Don't they do that? You have to build a car that goes up the ramp in a certain amount of time, you know? What is that?
But can we think about this? Like, in order to make it go at a constant speed, so the force is equal to mg times sine 20
Yeah, it is kind of like that. Yeah,
plus
yeah.
mu k, and
Plus, mu k, yeah. That is what this is.
it's the same thing.
That is mg sine plus that.
Hmm.
So the force is equal to that. Yeah, it's coming from there.
Oh,
But
it's
now
the same
we're
thing.
looking at it more from a power and energy view.
Okay.
Yeah,
That
exactly.
makes sense.
Yeah. So what is that? 0? 7.8 meters per second. Oh, that's pretty fast. With 40.5 watts, that's a lot of power. For a 1 kilogram car, yeah. That thing's gonna fly up that thing. It's like 15 miles an hour. That's probably unrealistic, right? Is the 9 volts too high? Or the 2 ohms is too low? Well, you could put a 9 volt battery, it's not that hard. But probably 2 ohms was too low to create something like that. It's gonna fly. Okay, then we can, of course, since the velocity is constant, we can find out how far it will have traveled. Just distance is v times t, right? So then it's just you take that v times t, and you get 15.6 meters. Hopefully you're the winner of that. So this gives you a little bit of an idea of application of it with power a little bit, and work, and then bringing in the work done by gravity. Okay, so on Wednesday then I'll cover potential energy, conservative forces, and equilibrium, stable versus unstable. Cool.